Yes, today class for the 2nd of April. This tape continues with what we were doing before. That is, we started correlational research design. And the strategy is you take subjects and you look at them at one point in time and you measure a number of characteristics and then you look at what the correlations are among these characteristics. That's how you test hypotheses. The most important correlational research design is the questionnaire or the poll. And last time we saw in the history of polling that polling in a scientific sense has been around for about 80 years. I would say the father of modern polling is George Gallup. It was George Gallup who made the discovery that you can make inferences from a sample to the larger population if your sample is representative. That's the beginning of scientific polling. Now, today I want to talk about sampling and sampling theory and the important calculation of the margin of error that we use to decide how close our sample is to the population. Now, what is a sample? Well, for a definition, a sample is a subset of a larger population, and we make inferences from that sample to the population. Usually, the researcher does not have the population at hand. They don't have that whole population. Why? Well, first of all, it's too expensive. Population can be very large. It would take a lot of money to try to actually ask questions to that whole population. Also, it would take a big organization to do that, and running a big organization makes for more errors. I know mathematicians that think you can get closer to what the actual facts are in a population if you have a sample of about 1,200 and you have a tight organization that you can control so that they accurately obtain data from that population. Uh, Also, it takes a long time to do the whole population, and time is often of the essence. You want your research done by a certain period of time. So these are the reasons why we take a sample. Now, some of the jargon that we use to decide sampling. What we do is we take, and I have here a chart that has this information. Uh, we're sitting out here in our research world here, and we're trying to figure out what's in the real world. That's the large population out there in the real world. So we can't do the whole real world, that whole population. So in our research world, we make inferences from what we get in our research world to that larger population. Now, in our research world, the subset of people in the population is called our sample. They're the people we're going to actually measure things about them. And in fact, we get information from that sample and we make inferences to that larger group. The population is what it's called, the large group out there that we're really interested in. Now, from that sample, we do various calculations and we generate the term statistics. Statistics like the mean income of our sample, things like that. Those summary kinds of pieces of information, those are called statistics in the sample. Uh, there are correlations to these statistics in our sample out in the population. We call those figures out in the population the parameters. So if we're looking at the mean income for American families, we might have a sample of 1,000 families. That mean is a statistic for our 1,000 families. But we're really interested in making inferences to what that figure is out in the population. That figure is called the parameter out in the population. And then finally, there's a convention that we represent statistics in our sample using Roman letters. So X bar is the mean, S is the standard deviation. Now, we're really not interested in those figures as much as what are they out in the population? What are those parameters? We use Greek letters for the parameters so that mu is the mean out there in the population. And we have sigma. Sigma is the standard deviation out in the population. So those are the pieces of the jargon that we use to make differentiations between the sample on the one side and the population on the other. Now, how do we draw the sample? Well, a sample begins with something called the sampling frame. The sampling frame is an actual or a theoretical list of all the units of analysis in the population. And sampling frames are prone to errors. When you have a mistake in your sampling frame, it introduces errors into your research. And I'll go over some of these problems people have with sampling frames, starting with incompleteness. Incompleteness is a problem in a sampling frame that when in fact some units that are in the population are not in your sampling frame. So you're going to introduce an error when you sample from that sampling frame. Take an example. Say you want to do a poll of people that live in the District of Columbia. I once worked on a piece of research in which we were interested in what do people in the District of Columbia think of the services that their city government performs, snow removal, garbage removal, things like that. So what if you wanted to do a random sample of 1,000 people in the District of Columbia? You could call them on the phone. You could use the phone book and randomly choose 1,000 people out of there. There's a problem with that. That is, the phone book is an incomplete sampling frame. That is, there are people who aren't in the phone book that are members of the District of Columbia. They're part of the population. You introduce an error by using a phone book. Another error in sampling frames that introduces problems is called clusters of elements. That is, when you sample and you're sampling people come in clusters rather than one by one. You can make an error in that way. Once in this 101 class, we did an exit poll. It was in November. We had a fall class, November election, and we did an exit poll in the election in Montgomery County for a member of Congress. So we have all these different polling places, and we want a random sample. We can't talk to everybody in Montgomery County. So what you might do is you could take all the polling places in Montgomery County, randomly choose one, and then we can give our questionnaire to, say, 500 people there. Well, there's a problem. This is called clusters of elements because not all of the polling places in Montgomery County are the same. You can randomly choose one, and what if it's Bethesda? The people in Bethesda tend to be more affluent than, say, the people in Frederick. They tend to be more democratic than the people in Frederick. So you introduce an error because you're taking clusters of elements from a sampling frame. Finally, there's a problem with sampling frames that introduces an error called foreign elements. That is, some of the units of analysis on the sampling frame aren't members of the population. That's a problem. Say you wanted to do, a sample of people in Howard County, registered voters in Howard County, where I live. Well, you can go up and get from the Howard County Board of Elections, you can randomly choose, say, 1,000 people. But some of those people have moved out of Howard counties, and these kind of registration records they're notoriously not up to date. So you can choose people, and you can actually call people who aren't in Howard County anymore. That would be foreign elements in your sampling frame, and that introduces an error. Now, samples really come in two kinds, a probability sample and a non-probability sample. Here's the difference. A probability sample is where you can say with exact mathematical certitude what the chances were that a person would be chosen to be in your sample. Take an example. If you were here at GW and we were doing our computer assignments, I would give you a data set from the American National Election Study. That's done by the University of Michigan. I was going to give you 1988. They randomly chose 2,487 voters in America to be in the American National Election Study. Now, what are the chances that any one American would be chosen to be in the American National Election Study? Well, they chose 2,487 people out of 190 million adults over the age of 18. That is, your chances of being selected in that sample were 2,487 over 190 million, or 0.00001, 1 out of 100,000. You can say with mathematical exactitude the chances that someone would be chosen to be in your sample. Then there's another group of samples. They're called non-probability samples, and you're not in a position where you can say with mathematical exactitude the chances that a person would be chosen to be in your sample. Let's look at a couple of non-probability samples. The first one is a convenience sample. You chose these people because they were conveniently there, and you gave them the questionnaire and you generated data in that way. That would be a convenient sample, would be if you stood outside the student union at GWU and you wanted a sample of 500 GW students and you gave out questionnaires outside the student union. Well, that was very convenient to do that sort of thing, but you could see how, well, you can't say exactly what the chances are that anyone would be in it, and you could see how you could introduce errors by doing it in that way. Remember we talked about the Literary Digest in the last video. That was the magazine that garnered together as many addresses as it could. It got 10 million addresses, and it sent out ballots or questionnaires to see how people would vote in 1936 in the presidential election. Well, that was a convenient sample too, because they conveniently had lists of people and their addresses that they wrote into their database. That's what a convenient sample is like. A second kind of non-probability sample is a purposive sample. That is, you choose this sample because you expect that the people that are going to be coming, that you're going to choose to be in the sample, are representatives of some larger population. So you purposely choose them. There is a voting district in California that, as far as the records go back, every year the person who won the presidential election in that place in California also won the whole state of California. So you could purposely sample people on election day doing an exit poll and making inferences to how California is going to go based upon that purposive sample. And finally, another non-probability sample is a quota sample. In a quota sample, you know the various characteristics that are important in your population, and then you choose people to fill in and have those representative numbers, the same proportion in your sample as in the population. So this is what George Gallup did in 1936. You know that, say, women are 54% of the population, men are 46. So in your sample, you have spaces where you're going to talk to 54% women, 46% males. If you knew that the population was 40% Republican, 40% Democrats, you'd make sure you had 40% Republicans and 40% Democrats. If you knew that the population was 30% rural, 30% suburban, 35 or 40%, whatever the number is there, city, then you purposely have those numbers. That's how a quota sample works. And it was powerful for George Gallup to do that sort of thing. Now, the important thing about a probability sample is that you can mathematically describe how big the error is, something called the margin of error. You've probably heard of the margin of error. You know what it means when someone says, we did a poll and Biden was beating Trump 49 to 47%. I saw a poll reporter the other day that said that. And that the margin of error in the poll is plus or minus 3 percentage points. What does that mean and where do they get that? That's what we want to talk about. The definition of the margin of error is the error in estimating population parameters due to sampling error. Now, here's the idea. You have your sample, you have a proportion, say, voting for Biden, 49%, but you're really not interested in your sample. You're interested in the population from where you've drawn that sample. And we want to know, how far off are we from that actual figure out in the population? We know we're probably not right on the money in our sample, and that's because there's something called sampling error. It isn't that the researcher made a mistake, but it's just the way it goes. When you take a sample, you're probably not going to exactly hit what's out in the population. And can we eliminate that? No, we can't. It's the nature of doing a sample, making inferences to the larger population based on your sample. So we can't really eliminate it. But what we can is we can reduce it and we can describe it. And that's what we do when we try to do scientific polling. Now, how do we calculate the margin of error? It depends upon the kind of question that you're asking. Some questions, like income, what is your family income? We take all that information and we get a mean for that question. And we want to know how close is the mean we have in our sample to what the mean is out in the population. That would be the calculation of the margin of error for a question in which you look at the mean. And this is I put down the way that we calculate the margin of error for the mean. The margin of error for the mean, x bar is what the mean represents. It's 1.96 times the standard deviation over the square root of n. The standard deviation is just a measure of how dispersed the cases are. N is always the number of cases in all of these formulas that we have. And then there's another kind of question where we're not interested in the mean, but we're interested in the proportion. That would be a question like, if the election were held today, would you vote for Biden or Trump? Well, what we'd get is for Biden, say, or for Trump, we would get a proportion, like 50%. And we want to know how close is that proportion to what the actual figures out in the population. And this is how we do a calculation of the measure of the margin of error for a proportion. It's 1.96 times the square root of PS times 1 minus PS over N, where PS is the proportion and N is the number of cases. So you have these two different formulas doing that. Now, let me give you an example of how this calculation could be done. First, the margin of error for the mean. And in this variable, what we're looking at is we want to know the income of people in the United States for families. And we have a random sample of 625 people, and we do a calculation of the mean, and it comes to $32,000. And we want to know how close is that $32,000 to what's actually out in the population. So we have in our example, N is 625. We have 625 cases. The mean, x bar, we came to 32,000. We did that calculation. Then we calculate the standard deviation. We'll talk about that at the end of the semester. That comes out to $5,000. So we stick these numbers into that formula I gave you. The margin of error for the mean is 1.96 times, we put $5,000 in for the standard deviation, over the square root of N, 625. And it comes out to $392. That's the margin of error of income in this circumstance. Now, how do we interpret that? That's what's important. What we do is we take a line like this and we put X bar was 32,000. Then we add one margin of error, $392, and we get $32,392. And we subtract one margin of error, we get to 31,608. How we interpret that margin of error is we're 95% sure the real figure out in the population is between 31,608 and 32,392. Does that make sense? What we do is we calculate a margin of error, we add one margin of error, we subtract one margin of error, and we get an interval. And we're 95% sure that that real figure out in the population is in that interval there. That would be an example of doing the margin of error for a mean. Now, I'm calculating here the margin of error of a proportion. That would be the question of, if the election were held today, who would you vote for, Trump or Biden? And let's say they do it in Ohio, and Trump gets 50%, and the pollster has polled 1,200 people. Okay, what we do is we stick in that formula I just gave you. The margin of error for a proportion is equal to 1.96 times the square root of PS times 1 minus PS over N, where PS is the proportion, 50%, and 1,200 is the number of cases. So we stick that into our calculator and we get 3 percentage points. The margin of error is 3 percentage points here. Now, how do we interpret it? Well, just like we did the proportion, we take the 0.50, that's what Trump got, we add one margin of error to it, that's 0.53. We subtract one margin of error for it, that's 0.47. So we have an interval between 47% and 53%. We're 95% confident that Trump's percentage actually in the population is between 47% and 53%. Now, how do we get the margin of error to be smaller? Think in your mind. We want the margin of error to be as small as possible. So we're closer to what the actual figure is out in the population, right? We want to squeeze this down. Look at this formula and see how can we make the margin of error shrink? And look at it for a second. Isn't it the case that if you blow up the number of cases and you interview more people, it's going to make the margin of error smaller? And doesn't that make sense? If you have more people in your sample, you're going to be closer to what the actual figure is out in the population. Now, can we eliminate this margin of error? As I said before, no, we can't, but we can make it smaller. And we can make it smaller by interviewing more people, making our sample size bigger. There's a downside to that, though, isn't there? As your sample size gets bigger, it's more and more expensive to do your research. So we have to balance how close do we want our margin of error versus how much money do we spend. And generally, I think in social science, we can live with a 3 percentage point margin of error for these kinds of polls we're looking at. The difficulty in a close election is that if Trump has 50%, and say Biden has 48%, 2% went to other people. They're the crazies out there. If Trump has 50% and Biden has 48%, we look at Trump's margin of error, it's between 45, 47, and 53. Well, the difference between Trump and Biden isn't larger than the margin of error. That's a situation in which you might hear a pollster say it's too close to call. The margin of error is so large and they're so close together that we're really not confident that the person who's ahead is really ahead out of the population. So that's how sampling works, and that's how we work with the margin of error. What you should do is go to the discussion section on Blackboard, make some comments, questions, whatever, and let me know how you're doing. Thank you. We'll come back Tuesday and we'll move on, and hopefully on Tuesday we can finish up correlational research design.